Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through wormholes and spaceships, through the old science fiction dream of crossing the galaxy in a vessel of light, and the stranger scientific dream of discovering that space itself may have hidden doors. For now, imagine a starship moving quietly through the darkness between stars. Its windows look out on a field of cold points, some blue, some amber, some so distant that their light began traveling long before any human city existed. The ship is fast by any ordinary standard. Its engines are steady. Its crew has charts, sensors, and a destination. Yet even in the richest stories we tell about starships, one problem always waits in the background. Space is not merely large. Space is patient on a scale that can make motion itself feel almost ceremonial. A real spacecraft can cross the distance from Earth to the Moon in days. A fast probe can cross the distance to the outer planets in years. Voyager 1, one of the farthest human-made machines ever sent outward, has been traveling since 1977. And after all that time, it has only just entered interstellar space. It has not reached another star. At roughly its present speed, the nearest star system beyond the Sun would still be tens of thousands of years away. A spaceship, even a brave one, still has to pay the price of distance. A wormhole offers a different kind of dream. It does not make a ship faster in the usual sense. It does not ask the ship to race across every kilometer between here and there. It asks whether the geometry of space-time might contain a shortcut, a tunnel, a bridge, a second path between two far regions that are distant along the normal route but close through a hidden passage. If a spaceship is a lantern carried across a long, dark field, a wormhole is the possibility of finding a door in the side of the night. That is why wormholes have become one of science fiction's most graceful devices. They solve the distance problem without turning every journey into an impossible acceleration. A ship enters one mouth of the passage near one star, travels through a region where the usual map no longer applies, and emerges somewhere else entirely. A voyage that should require centuries becomes a crossing that fits inside a scene. The story can move from one side of a galaxy to another without pretending that ordinary engines have conquered the speed of light. In Star Trek, this idea becomes especially memorable near the planet Bajor, where a stable wormhole links the familiar Alpha Quadrant to the distant Gamma Quadrant, roughly 70,000 light-years away. Around that opening sits Deep Space Nine, a station that becomes not only a port, but a threshold. Ships approach the mouth of the wormhole as if approaching a harbor entrance. They pass through a brilliant interior, and moments later, they are beyond an enormous galactic distance that would otherwise swallow whole civilizations in travel time. The Bajoran wormhole is beautiful storytelling because it is not treated only as a machine. To Starfleet officers, it is a navigational discovery, a natural corridor through space. To Bajorans, it is the celestial temple, the home of beings they call the prophets. To traders, soldiers, explorers, and governments, it is a route that changes the balance of power. A single passage in space becomes a place where science, faith, strategy, and wonder all meet. That is exactly what a real wormhole, if one existed in reachable space, would do to us. It would not simply shorten a journey. It would change what a map means. The interaction between starships and wormholes in those stories also reveals an important difference between two famous science fiction solutions to distance. Warp drive lets a ship choose a direction and travel from one star to another, bending the rules of motion in a way that belongs to the ship itself. A wormhole belongs to spacetime. It is a fixed route, or at least a route with its own geography. A starship may be able to approach it, enter it, study it, guard it, mine it with defensive fields, or lose it when it collapses, but the ship does not own the shortcut. The shortcut is a place. That single distinction makes wormholes feel more natural than engines. An engine is an achievement. A wormhole is a discovery. It is like finding a mountain pass through a range that had seemed uncrossable, or a sea route between continents that changes every trade map drawn afterward. The ship still matters, but the greater marvel is the shape of the world around the ship. Star Trek returns to this distinction again and again. Some wormholes are stable enough to become political geography, like the Bajoran Passage. Others are brief and uncertain. The Barzan wormhole, in one well-known story, appears valuable because it seems to offer a permanent route to the far Delta Quadrant, until careful investigation shows that one end is unstable, shifting dangerously from place to place. A route that looks like a bridge becomes more like a loose thread in a moving fabric. A vessel can enter, but return is no longer guaranteed. In another story, a tiny wormhole offers Voyager, stranded far from home, a chance to speak across an impossible distance. The passage is too small for the ship, and stranger still, its far end connects not only to another region of space, but to a different time. The crew can send a message, but not a rescue. The wormhole is not a highway. It is a narrow, imperfect opening, a faint conversation through curved space-time, useful and heartbreaking at once. There are also moments when a wormhole is less a road than a hazard. A starship may be drawn toward an opening before its crew understands whether the passage is stable, where the far end leads, or whether the geometry inside obeys the expectations built into their navigation computers. In ordinary travel, a captain worries about fuel, velocity, obstacles, and arrival time. Near a wormhole, the deeper worry becomes the reliability of the road itself. A bad engine leaves a ship stranded in space. A bad shortcut can make the word stranded too simple, because the ship may no longer share the same map, the same year, or the same causal order as the place it left. The Bajoran wormhole avoids most of these problems by being unusually generous. It has a stable mouth near Bajor, a stable far mouth in the Gamma Quadrant, and a passage large enough for starships. That makes it almost the best possible version of the wormhole dream. It behaves less like a brief natural anomaly and more like a permanent canal through space-time. Much of Deep Space Nine's story grows around controlling, respecting, defending, and interpreting that canal, which is a quiet recognition of how powerful a real shortcut would be. The science fiction is not realistic in every detail, but it understands the central consequence. When geography changes, history changes with it. These fictional variations are surprisingly helpful. They remind us that a wormhole is not one simple thing. It could be large or small, stable or unstable, passable or only able to transmit light and signals. It might connect distant places, different times, or, in the more speculative edges of mathematics, even different universes. Most of those possibilities remain unobserved. Some may be impossible. But the vocabulary of fiction gives the mind a set of pictures, and pictures are often how difficult science first becomes approachable. To understand what physics actually says, we have to return from the station window and the starship bridge to a quieter place. A sheet of paper, a pencil, and the strange equations of general relativity. Before Albert Einstein, gravity was usually described in Newton's language as a force between masses. The sun pulled on Earth. Earth pulled on the moon. Every object with mass attracted every other object with mass. This picture worked beautifully for many purposes, and it still works well enough for countless practical calculations. Einstein changed the deeper meaning of the picture. In General Relativity, completed in 1915, gravity is not best understood as an invisible hand reaching across empty space. Gravity is the curvature of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. A planet orbits the Sun not because it is being pulled along a hidden string, but because it is following the straightest available path through a geometry that the Sun has curved. The familiar fabric analogy is imperfect but useful if handled gently. Imagine a smooth sheet stretched across a frame. Place a heavy sphere near the center, and the sheet curves downward. A marble rolling nearby does not need a tiny motor to turn toward the sphere. It follows the curved surface. Real space-time is not a two-dimensional cloth dipping into a third dimension, and gravity is not literally a dent in a sheet, but the image helps preserve the essential idea. Matter changes geometry, and motion follows geometry. Once gravity becomes geometry, a new question becomes thinkable. If space-time can bend, can it also connect in unusual ways? Can two regions that are far apart along one route be near along another? Can the universe have a tunnel through its own structure, not a tunnel carved through empty space, but a tunnel made from space-time itself? The first path toward that question appeared almost immediately after Einstein published his theory. In 1916, Karl Schwarzschild found an exact solution to Einstein's equations describing the space-time around a perfectly spherical, non-rotating mass. That solution later became central to black hole physics. It included a boundary, now called the Schwarzschild radius, the size at which a mass becomes so compact that not even light can escape from within it. A star compressed past that boundary becomes something very different from an ordinary star. It becomes a black hole. Almost 2 decades later, in 1935, Einstein and Nathan Rosen studied the mathematics of the Schwarzschild solution and noticed a strange structure. The equations could be interpreted as describing a bridge between two separate regions of space-time. This Einstein-Rosen bridge is the ancestor of the modern wormhole idea. It was not originally a practical travel proposal. It was a mathematical structure hiding in the geometry of black holes, a narrow throat connecting two regions in a way that seemed possible on paper. The word wormhole comes from a simpler image. A worm crawling across the surface of an apple must travel the long curved route from one side to the other. A worm tunneling through the apple takes a shorter path. The apple's surface has not shrunk, but the route has changed. In the same way, a wormhole would not make Alpha Centauri physically drift closer to Earth through normal space. It would provide another route through a deeper geometry. But the first Einstein-Rosen bridge was not a starship corridor. It was unstable. It would pinch off too quickly for anything to cross. Even describing what happens near it requires idealized conditions far removed from real astrophysical black holes, which form from collapsing stars, spin, interact with matter, and live in a universe full of radiation, fields, and disturbance. The earliest bridge was more like a clue than a road. This is where careful language matters. General relativity allows certain wormhole-like solutions. That does not mean the universe is full of usable wormholes. Mathematics can describe many possible geometries, and nature is allowed to be more restrictive than our equations at first appear. A doorway drawn correctly on a map is not the same thing as a doorway built in stone. Still, Physicists did not stop at the original bridge. In 1988, Michael Morris and Kip Thorne described a class of traversable wormholes in a serious physics paper. Their question was not whether wormholes made good stories. Their question was what the laws of relativity would require if a wormhole were to be held open long enough and gently enough for a traveler to pass through. The result was not a recipe for engineering. It was a careful boundary line between imagination and known physics. The central difficulty is the throat. A wormhole throat would tend to collapse unless something held it open. Ordinary matter and ordinary energy curve spacetime inward in familiar gravitational ways. To keep a traversable wormhole open, most models require exotic matter with negative energy density. In simple terms, the wormhole would need something that acts gravitationally unlike the matter we know, something able to resist the throat's collapse and keep the passage from becoming a sealed horizon or a crushing singularity. Negative energy is not just a decorative phrase. In quantum field theory, small negative energy effects can appear under special conditions. The Casimir effect, measured in laboratories, involves two closely spaced conducting plates in a vacuum and produces a tiny force associated with changes in the vacuum energy between them. This does not give us a barrel of exotic matter. It does not make a spacecraft-ready bridge. It only shows that the quantum vacuum is stranger than empty space sounds and that tiny negative energy densities are not meaningless words. The leap from a minute laboratory effect to a stable wormhole large enough for a starship is enormous. It is not like improving a canoe into an ocean liner. It is closer to noticing a single snowflake and asking whether it could hold open a mountain. The measured effects are real, but the scale required for a useful traversable wormhole may be beyond anything nature permits in controllable form. This is why honest wormhole science lives in a delicate place. It is not pure fantasy, but it is not established travel technology either. A starship approaching a real wormhole, if such a passage existed, would face questions far more severe than choosing a course. First, the ship would need to know whether the throat is stable. If the geometry changes too quickly, the ship could be trapped, stretched, crushed, or simply find that the exit is no longer where it was expected to be. Fiction often turns this into drama, with sensors fluctuating and crews making quick decisions. Real physics turns it into geometry, energy conditions, tidal forces, and causal structure. Tidal forces would matter because gravity changes from place to place. Near Earth, the difference between the gravitational pull on your head and your feet is tiny. Near a compact, massive object, that difference can become enormous. A wormhole designed for safe travel would need the tidal forces at its throat to be small enough that a ship and anything inside it could cross without being pulled apart. The throat would also need to be wide enough to avoid collisions with the passage walls, if walls is even the right word for a region of curved spacetime. There is also the question of navigation. A wormhole mouth might behave gravitationally like a massive object. Light from stars behind it could bend around it. The view through the mouth might show the sky at the other end, distorted into rings and arcs by curved spacetime. From outside, it might not look like a glowing tunnel. It might look like a lens, a dark sphere, or a region where background stars are rearranged in a way that refuses to match ordinary gravity. This is one reason astronomers have considered gravitational lensing as a possible way to search for wormholes. Gravitational lensing is real and well observed. Massive galaxies and galaxy clusters bend the light of more distant objects behind them, sometimes forming arcs or near-perfect rings. These Einstein rings are not wormholes. They are gravity acting as a natural telescope. But a wormhole, if it existed, might create its own distinctive lensing signature. Instead of seeing the wormhole directly, astronomers might notice that the background sky around it is being bent in an unusual way. The difficulty is that the sky is already full of things that bend, dim, flare, and disguise light. Ordinary stars can act as gravitational lenses. Black holes can lens background stars. Galaxies and clusters can split a distant galaxy into several images. Dust can hide light. Variable stars can brighten and fade. A wormhole search would have to separate a truly exotic signature from a crowded sky of ordinary explanations. That is why any claim of a wormhole would need extraordinary caution. It would not be enough to find a strange distortion. Astronomers would need a distortion that fits a wormhole better than a black hole, a galaxy, a star, an instrument artifact, or a chance alignment. If a candidate ever appeared, the first response would not be a crude mission. It would be patient observation. Telescopes at different wavelengths would study the region. Astronomers would watch how background stars change over time. Radio instruments might search for unusual signals. Gravitational models would be tested against the data. If the candidates seemed close enough, robotic spacecraft might one day be imagined, but even that belongs far beyond our present technology. The first real wormhole discovery, if it ever came, would probably begin not as a glowing doorway in a window, but as a stubborn pattern in a dataset that refused to behave like anything else. So far, no confirmed wormhole has been observed. No telescope has found a stable passage to another star. No gravitational lens has demanded a wormhole explanation. The absence of evidence is not a proof of impossibility, but it is important. In a sleep-friendly science story, wonder should not blur the line between a door that exists in fiction, a solution that exists in mathematics, and an object that has been observed in the sky. The Bajoran wormhole is a vivid fictional doorway. A traversable wormhole is a permitted but deeply difficult theoretical structure. A real observed wormhole is, for now, absent from astronomy. The speed of light gives the whole subject its emotional weight. In ordinary space, nothing with mass can accelerate to light speed, and no signal carrying information can locally move faster than light in a vacuum. This is not only a speed limit for engines, it is woven into the structure of causality, the ordering of cause and effect. If a star explodes 100 light-years away, Earth cannot know it happened until the light or some other signal has had 100 years to arrive. A wormhole appears to cheat that limit, but the details are subtle. A traveler passing through a wormhole would not necessarily be moving faster than light locally. Inside the passage, the ship may travel at ordinary sublight speed through a short route. The apparent faster-than-light effect comes from the shortcut. The normal path through outside space may be thousands of light-years long, while the route through the wormhole is brief. It is the map, not the ship's local speedometer, that has become strange. This is why wormholes are so tempting in fiction. They preserve the dignity of the speed of light while still allowing interstellar stories. The ship does not outrun light in its immediate surroundings. It slips through a geometry where far places have been connected. In storytelling terms, the result feels almost fair. The universe keeps its rule, and the story finds a hidden hallway. But causality is not easily fooled. If the two mouths of a wormhole can move relative to one another or sit in different gravitational environments, then relativity tells us their clocks may drift apart. One mouth can age differently from the other. In some theoretical arrangements, a traversable wormhole could become a time machine, allowing a traveler to enter one mouth and emerge from the other at an earlier time according to the outside universe. This is where the quiet geometry of shortcuts touches the deep unease of paradox. Physicists take this seriously, not because they expect starship crews to meet their past selves next week, but because a theory that permits closed loops in time has to face hard questions. Could a signal prevent its own sending? Could a traveler alter the conditions that allowed the journey? Stephen Hawking famously proposed a chronology protection conjecture, the idea that the laws of physics may prevent time machines from forming even if the equations of general relativity seem to allow them in special cases. The conjecture is not a completed proof, but it expresses a deep suspicion shared by many physicists. Nature may protect causality. Star Trek stories often use wormholes exactly at this border. A ship does not only cross space, it sometimes brushes against time. An unstable passage creates a meeting that should not happen, or a message arrives from the wrong year, or an exit is not only far away but displaced in history. These are dramatic inventions, but they are not random inventions. They grow from the real relationship between space-time geometry, motion, gravity, and clock rates. Time dilation itself is not speculative. It has been measured. Clocks moving at different speeds or resting in different gravitational fields do not always agree when reunited. GPS satellites must account for both special and general relativity to keep navigation accurate. Without those corrections, position calculations on Earth would drift. That everyday dependence on relativity is one of the loveliest facts in modern science. The same theory that lets physicists write down the possibility of a wormhole also helps a phone know where it is. General relativity has passed many other tests as well. During the solar eclipse of 1919, starlight passing near the Sun was observed to bend in the way Einstein predicted. More recently, LIGO detected gravitational waves from merging black holes, ripples in space-time itself arriving after a journey of more than 1 billion years. These confirmations do not prove wormholes exist. They strengthen confidence in the broader theory whose equations permit them. It is as though the language is trustworthy, even when some of the sentences written in that language describe things we have not found. This is an important distinction for a calm science story. The tested parts of relativity are not fragile. They are woven into astronomy, spacecraft tracking, black hole observations, gravitational wave astronomy, and practical satellite navigation. But a trusted theory can still contain special solutions that nature may never realize. The equations of fluid motion can describe ideal waves that no real ocean holds forever. The equations of relativity can describe unusual spacetimes that may require impossible ingredients. A wormhole is strongest when described with both truths at once. It grows from serious physics and it remains unconfirmed. Black holes sit near wormholes in both mathematics and imagination. A black hole is a region where space-time has curved so strongly that anything crossing the event horizon cannot escape to the outside universe. Real black holes are observed through their effects. Stars orbiting unseen massive objects, hot accretion disks, jets, gravitational waves from mergers, and the shadow-like images produced by the Event Horizon Telescope. They are no longer only theoretical. They are part of the working landscape of astronomy. Wormholes are different. They are not black holes with convenient exits. The image of falling into a black hole and emerging somewhere else is, in most real cases, not supported by what physicists expect from astrophysical black holes. A stellar black hole, formed from a collapsing massive star, is not believed to contain a safe passage to another region. Its interior, as described by classical relativity, leads toward a singularity, a place where the theory itself points to its own breakdown. A traversable wormhole would require a very different structure, held open by conditions not known to exist in nature at useful scale. This distinction matters for a starship story. A crew can orbit a black hole, study its accretion disk, watch light bend into rings, and measure time dilation near it. But entering a real black hole is not the same as entering a wormhole. One is an observed kind of cosmic object with a boundary of no return. The other is a hypothetical bridge whose safe existence would require unusual matter and carefully arranged geometry. The fiction sometimes softens that difference because stories need images. A spinning black hole can look like a gateway. A tunnel of light can stand in for curved space-time. A ship can cross a threshold and make the invisible visible. These images are useful as long as we remember their limits. The real universe does not owe us door-shaped wonders. It may prefer quiet signatures in data, faint distortions in starlight, and equations that take decades to interpret. If a wormhole did exist naturally, where might it be? The honest answer is that we do not know. It might require conditions from the early universe when space-time was hotter, denser, and more violently curved than it is today. It might be connected to quantum gravity, the missing theory that would unite the smooth geometry of general relativity with the probabilistic world of quantum mechanics. John Wheeler once imagined that at extremely tiny scales, space-time might be foamy, full of fleeting fluctuations, perhaps even tiny wormhole-like structures appearing and vanishing too quickly for any ordinary object to use. Quantum foam is not a subway system for particles. It is a speculative picture of what space-time might be like near the Planck scale, far below anything we can directly image. Still, it points to a possibility that is both humble and strange. The universe may be smooth at human, planetary, and stellar scales, while at the smallest scales, its geometry may be restless. If microscopic wormholes exist there, they would not resemble the grand, glowing corridors of fiction. They would be brief, tiny, and inaccessible, more like sparks in the texture of reality than bridges for ships. A useful way to compare spaceships and wormholes is to ask what each one must bring to the journey. A spaceship must bring energy, shielding, navigation, life support, propulsion, and time. It must endure the long path. A wormhole must bring geometry. The starship crosses because the route has already been made short. The ship's engineering problem becomes a problem of approach, stability, and survival, while the deeper impossibility has been moved into the structure of space-time. That trade is not necessarily easier. To build a starship that reaches another star within a human lifetime is fantastically hard. To build a wormhole may be harder in a more fundamental way. A starship asks for better engineering within known physics. A traversable wormhole may ask for matter and energy arrangements we do not know how to create, perhaps cannot create, and may never find. One dream is an extension of engines. The other is an argument with geometry. Yet the wormhole dream keeps returning because it touches something older than physics. Human beings understand doors. We understand paths through walls, bridges over rivers, tunnels under mountains, harbors through storms. A wormhole turns the universe itself into a landscape with hidden passes. It gives distance, a secret architecture. It lets a tiny vessel face a galaxy, not by becoming infinitely fast, but by finding the one place where the galaxy has folded. The scale of what would be saved is almost difficult to keep in mind. Light from the Sun takes a little over 8 minutes to reach Earth. Light from Neptune takes hours. Light from Proxima Centauri, the nearest neighboring star system, takes more than 4 years. A radio message sent there would require more than 4 years to arrive, and more than 4 years for the answer to return. That is our nearest stellar neighbor. The Milky Way is about 100,000 light-years wide. The Bajoran-style distance of 70,000 light-years is not a dramatic exaggeration of galactic scale. It is a genuine fraction of our galaxy. For a real spacecraft, 70,000 light-years is not merely a long mission. It is almost another category of existence. Civilizations rise and fall on timescales shorter than such a crossing at ordinary speeds. Languages change, continents shift slowly, stars themselves age. A stable wormhole across that distance would be more than transportation. It would turn a remote region of the galaxy into a neighbor. This is why control of a wormhole becomes so important in fiction. Whoever controls the passage controls a route no fleet can simply duplicate. 1,000 starships still have to cross space unless they can use the bridge. The bridge changes economics, diplomacy, defense, exploration, and identity. A station near the mouth of the passage becomes a gatehouse for a civilization's future. Even in a calm scientific reading, that part of the fiction makes sense. Geography shapes history, and a wormhole would be the most extreme geography imaginable. The same logic would apply if astronomers found a small, natural wormhole that only transmitted light. It might not carry a ship, but it could still let us see a region otherwise unreachable. It could become a telescope through space-time, a window rather than a road. If one mouth opened near Earth and the other opened far across the galaxy, the view through it might show stars whose ordinary light would take ages to arrive. Even a non-traversable or barely traversable wormhole could transform astronomy if it allowed information to pass. But again, the caution returns. Information through wormholes also raises causality questions. If signals can take shortcuts that beat light along the outside route, then the ordering of events can become frame-dependent in troubling ways. Relativity does not treat time as a universal background shared by everyone. Observers moving differently can disagree about the timing of distant events. That is harmless in ordinary circumstances because no information outruns light. Wormholes, if arranged incautiously, press directly on that protection. Some physicists suspect that quantum effects near a would-be time machine might grow without bound, destroying the wormhole or preventing the closed time loop from forming. Others explore whether certain wormholes could exist without creating usable paradoxes. The work is technical, ongoing, and unresolved. For narration, the cleanest statement is simple. Wormholes are mathematical possibilities in general relativity. Traversable wormholes require exotic conditions, and time travel versions create severe problems that may be forbidden by deeper laws. The words deeper laws are important because general relativity, powerful as it is not believed to be the final description of nature. It does not include quantum mechanics in a complete way. Near singularities, near the Planck scale, and perhaps near the throat of a wormhole held open by quantum fields, we need a theory of quantum gravity. We do not yet have one confirmed by experiment. This means that some wormhole conclusions may change when that deeper theory is found. They may become more possible, more impossible, or simply different from the pictures we use now. This uncertainty should not make the subject feel weaker. It makes it more honest. Science is not a catalog of finished answers. It is a careful way of separating what has been observed, what has been tested, what follows from trusted mathematics, what remains model-dependent, and what belongs to speculation. Wormholes occupy several of those shelves at once. Curved spacetime is established. Black holes are observed. Gravitational waves are observed. Einstein-Rosen bridges are mathematical structures. Traversable wormholes are theoretical models. Starship passages through them are fiction built on a real question. There is a quiet pleasure in letting those categories remain distinct. The fiction does not have to be true to be valuable. It gives the mind a scene, a ship, a station, a luminous mouth in space. The sudden presence of a far quadrant where ordinary travel would have found only centuries of darkness. The science then steps beside the scene and says, here is what space-time really does. Here is what the equations allow. Here is what we have measured. And here is where the door is only chalk on the wall. Imagine again the starship near the wormhole mouth. Outside, the stars of one region shine. Through the passage, if it is transparent, another sky may appear, not as a flat picture, but as a warped and curved view from somewhere else. The ship does not need to know every equation to experience the crossing, but the crossing, if it were real, would be an act of trust in geometry. The crew would be trusting that the throat remains open, that tidal forces stay gentle, that radiation does not surge, that the exit is where the map says it is, and that the passage does not place them in conflict with causality itself. A real mission plan would be cautious beyond anything fiction usually has time to show. Before a crewed ship ever approached, robotic probes would go first. They would map gravitational fields, send signals, test clock synchronization, measure radiation, and perhaps release small instrument packages through the throat. Mission control would wait to see whether signals return from the expected exit, whether clocks disagree, whether the passage magnifies or distorts radiation, whether the wormhole mouth moves, spins, or fluctuates. The first great wormhole voyage would begin not with a dramatic command, but with months or years of careful measurement. Even then, a starship would need to decide how to enter. Should it approach slowly, or does the geometry require a particular trajectory? Does the mouth have a safe orbital zone, like the space around a planet, or is the region around it unstable? If the exit lies near another star, a black hole, or a dense cloud of gas, the ship could emerge into a hazard that the entrance side cannot reveal completely. A wormhole shortens distance, but it does not remove the need for ordinary navigation. The far side is still a real place with gravity, radiation, dust, planets, debris, and motion of its own. Communication would be another quiet challenge. If signals can pass through the wormhole, then the two mouths become a communications link across impossible distance. If signals cannot pass reliably, every crossing becomes more solitary. A probe might enter and disappear from the entrance side until it returns. If the two mouths age at different rates, time stamps on messages become part of the science. The mission would need to know not only where the probe emerged, but when, according to both ends of the passage. Fiction often uses this for wonder or tension. A real mission would make it a clock comparison and a careful argument about simultaneity. If the passage were stable, the next question would be ownership. Though ownership feels like a very small human word beside such a thing. A wormhole mouth in space would be a natural resource, a scientific instrument, a transportation route, and a possible hazard all at once. It could connect friendly regions or dangerous ones. It could bring knowledge or invasion, trade or contamination, rescue or conflict. Deep Space Nine understood this intuitively. A bridge is never only a bridge, it changes what can arrive. The real universe gives us milder examples. Mountain passes shape nations, canals reshape trade, ocean currents guide migration and weather, railroads and air routes alter cities. The difference is scale. A wormhole would make geography interstellar. It would place two separate neighborhoods of the galaxy into daily relation. The night sky on one side would become the doorway to the sky on the other. There is also a philosophical softness in the idea. A spaceship expresses effort across distance. A wormhole expresses relation beneath distance. It suggests that the universe may be connected in ways not visible from the ordinary surface of the map. That is not a claim that wormholes exist. It is the feeling the idea carries, and perhaps the reason it has lasted so long in both physics and storytelling. Even if traversable wormholes never exist, studying them has value. They force physicists to ask what general relativity permits, what quantum fields forbid, what energy conditions really mean, and how causality survives in curved space-time. They clarify the difference between mathematical possibility and physical reality. They connect black holes, quantum theory, time dilation, negative energy, and cosmic censorship into one strange conversation. A good impossible idea can still be useful if it shows exactly where the boundaries are. This is true of science fiction as well. A starship crossing a wormhole is not evidence, but it is a compact image of several deep questions. Can space have topology, a connectedness more complicated than ordinary emptiness? Can time behave differently at different mouths of a passage? Can a shortcut exist without violating the local speed of light? Can exploration depend not only on better engines, but on unexpected structure in the universe itself? The fictional ship carries those questions in a way a quiet equation cannot always do alone. As the episode draws toward its softer end, it may help to hold the comparison one last time. The spaceship is the traveler. The wormhole is the route. The spaceship asks how far courage and engineering can go. The wormhole asks whether distance is as final as it seems. The spaceship moves through space. The wormhole changes the available paths through spacetime. Together, they form one of the richest dreams in modern cosmic storytelling, not merely to travel faster, but to discover that the universe has hidden architecture. The known universe remains silent on whether such architecture exists at useful scale. No observatory has confirmed a wormhole. No probe has entered one. No exotic matter reservoir waits in a laboratory. The obstacles are not small. They are deep, mathematical, physical, and possibly final. Yet the question remains clear enough to study, and there is peace in that clarity. A door can be unbuilt and still teach us what walls are made of. Hypnos walks once more beside the imagined station, where ships wait at the edge of a luminous passage. In one direction lies the familiar side of the galaxy, mapped by old routes and known stars. In the other lies a distant quadrant, suddenly near because the story has allowed space-time to fold. Around the scene, real physics stands quietly, neither approving everything nor taking the wonder away. It says only that space and time are not rigid scenery. They bend, they stretch, they ripple, they slow clocks and curve starlight. Under some mathematical conditions, they may even form bridges. That is enough for tonight. Enough to picture a starship not racing through every mile of darkness, but pausing before a threshold. Enough to remember that the speed of light still guards causality, that general relativity still shapes our satellites and our black hole images, and that wormholes, if they exist at all, belong to the most delicate edge between imagination and theory, enough to let the idea remain open without forcing it to become certainty. Somewhere beyond the ordinary map, the stars continue as they always have, separated by distances that give the galaxy its grandeur. Somewhere inside the equations, a narrower path may be sketched, faint and unconfirmed, a bridge whose stones are not stones at all, but curvature, energy, and time. A spaceship can wait beside that sketch, a story can enter it. Science can study its outline, and Hypnos, patient at the doorway, can let the question rest there, softly unresolved, while the night holds both the long road and the possible shortcut in the same quiet dark. The Hypnos Sleep Channel will return with another journey soon, into another place where fiction and reality meet beneath the stars. For tonight, the starship, the wormhole, and the patient geometry of space-time are enough.